All right, so today, as I said on Tuesday, I'm going to uh, do a recap of what we have seen up to now. So it will be a fast review of what we have covered up to now. And if you have any questions, I'll be happy to answer your questions as well. You may have seen the announcement I made yesterday. We have a small mini midterm exam so that you get acquainted with the types of questions that you may face in the midterm exam, and you may attempt that many times. And the actual midterm exam is you'll only have one chance to attempt it. It's going to be on Sunday at 6 p.m. And it will be available again on AutoClass at the top of the page. When you log in AutoClass, you'll be able to see the midterm exam, and you'll be able to start your attempt starting at 6 p.m. This Sunday. Before we start, do you have any questions about any topic? Do you have any certain specific topics that you want me to go over the second time? You may use the chat box if you want, I mean, you can. I mean, if as I go along, if you have some ideas about some specific topic requests, please let me know, and I will go over them in more detail. But let me quickly recap what we have seen up to now. So we start with the semester with images and displays, but in that regard, we just had some general ideas like how do we represent images, what is about the hardware, the gamma correction, resolution of images, and how do we represent color, different channels, the RGB, the color space. So it was images and displays was mostly this textbook knowledge. Then we talked about our first algorithm, ray tracing algorithm. And I mean, this whole semester, computer graphics is all about, especially three-dimensional computer graphics, is all about generating a photograph of a virtual world. So we started with our first algorithm in that regard, ray tracing, which just we have some virtual world which may be composed of some spheres and some triangular meshes. And what we had a camera, an image window, which looks in which all the rays coming through these pixels pass through this image window, pass through the centers of pixels. So the ray tracing algorithm simply is, for each pixel, compute the color. That's the basic algorithm. Compute the color of each pixel. And here it's basically trying to simulate physics in such a way that in real life, light rays. Wow, you can now see my screen. It's like I started sharing my screen. Did you just start seeing my screen right now? Or is Zoom giving me feedback a little bit late? So I don't know. I mean, if you could see, yeah, probably it was Zoom. I mean, I just had on my screen feedback from Zoom saying that the participants now can see your screen. Okay. Yeah, the feedback was late. That's a good error. Anyway, so here, yeah, the goal was to simulate the physics of what happens in real life. I mean, light rays come into our retina, and the photosensitive cells pick that up, and cognition occurs in the brain. We actually do not care about that much in cognition, so this is not a cognitive science course, computer graphics. Our goal is just to generate simulate the thing that happens in the retina, on the retina. Or you may also think about that we are not actually trying to simulate the biology, but we are trying to simulate actual cameras, the cameras on your smartphones or your camera or your professional or semi-professional SLR cameras you may have, which if you're interested in photography. So we are trying to simulate that actually, and in that the photograph has a lens, and the light rays go through that lens and are collected on a sensor chip. There is a chip in digital cameras. there's a chip that collects these photons. So, and these signals are then turned into colorful pictures. Okay, so we are trying to simulate that, and in that regard, our goal is to compute the color of each pixel here. And what we do is, in ray tracing, what we did was we had all these parameters: the gaze direction, gaze, the up vector. So it's actually, the camera has its own local coordinate system. It has gaze, up vector, the u-axis, and the w-axis. So it is a coordinate system where in which this eye point is at the origin. And the first thing that we tried to solve was, what is if I have an image window which is like a certain distance away from this camera? What will be the coordinate of the center of this pixel? That was the first thing we solved, and we did this by doing some vector algebra, by adding some vectors, subtracting them. For example, if you know the if you know your gaze vector, and if you know the distance from your image, if this gaze direction is given to you as a unit vector, then simply the center of this image window, it's not necessarily the center of the pixel at the, there may not be a single center pixel if your resolution is an even number resolution, okay, in both sizes, in any of the sizes. If you have a resolution which is like 1000 by 500, for example, the center of the image window will happen to be at the corner of 4 pixels, okay. So there will, it will be the center of the image may actually be somewhere here, right? So the first thing that we do is find the center of this image window, which is not, as you can see, not necessarily the center of the pixel. Okay, so, and we find this by assuming that our image window is orthogonal. There's 90-degree angle. So in other words, if you start with location E and go in the gaze direction, which was a unit vector, distance times distance, let's call it this. If you go this, start from here, go this much in the gaze direction, you're going to end up here at this point M. And then, for example, if you know the left and right boundary, so the other parameters we were given was the left, right, top, bottom boundaries. So if you go, for example, in the U direction also tells me how you move on the image window. So all these assumptions actually are valid only, I mean, if our ray pixel coordinate computation algorithm is valid only if our image window is actually parallel to this UV plane or XY plane of the camera. If it's not parallel to the UV plane, if it's then it will be complicated. We need to have, I mean, just the distance would not be sufficient. Okay, first of all, if you want to have an image window in which you want to have a complicated image window which is not orthogonal to your gaze, then you need to specify the direction it's looking at, or you need to specify its 4 corners as coordinates. For example, it would have a different normal vector. So we haven't seen that, okay? That's complicated. We had a simple image window which is just defined by this distance, okay? The image window by this distance and boundaries, left, right, top, bottom boundaries. So our gaze is orthogonal, so which means that going left to right on the image window in the pixels is determined by your x-axis. Your u vector, which is your x-axis, tells you which direction on this image window is you go right on a row of pixels. And this v vector, the up vector, similarly shows you which directions you go up in a column of pixels, in a single column of pixels, which direction is up. This is that v and u are those directions. So in other words, if you go in the u direction, if you go to the left boundary, which is a negative number, for example, left boundary is like -2, right boundary is 2. So if you go -2 units in the u direction, starting from M, it will get you to the left edge of your image window. Similarly, if you go, for example, 1 unit, if it was, I mean, if the top boundary is 1 and bottom boundary is given as -1. By the way, this 1, -1, -2, 1, these are not coordinates, as you can see. They're given as Distances, relative distances from the center of you may think about this as the center of the image window, or the distance from your camera to the left, to the right, and to top and to bottom. So these are relative distances, but which are given as the negative numbers, -2, meaning that the left boundary is 2 units to the left of this eye. Okay, so these are just assumptions, just heuristics. I mean, we could have given the entire image plane, as I said, with different parameters. We could have written we could have given the 4 corners as coordinates, and you would find whether the boundaries yourself. But yeah, this is how the parameters are given to us. And in that regard, for example, if you go 1 unit also to in the v direction, okay, so u direction, v direction are these. This is u, this is v. And we find ourselves at this top left corner, which is not again the center of pixels. So, but after we get here, the method that we used to find the center of the pixels was you get an ij pixel coordinate which starts at 0, 0 in the top left pixel. So this, because if this is your top left corner of the image, this becomes your 0, 0 pixel is this location, as you can see, which is 0.5 pixel width in the u direction, and you also go in the -v direction, 0.5 half pixel height. So based on what ij are, we are just going to be adding either 1.5 pixels to the pixel width to the left, 1.5 pixels down. So the rest is just getting the pixel width and height into this equation and going on the image plane left and right, which is given again by your u. By the way, after you're here, going right is still in the u direction, but going down, as you can see, v direction was the up direction, going down will be -v. So that's why we have this. Let me go to the slides. Here is ray tracing geometry. That's why we have, where is that? So here, that's why we have this minus in front of this v, because we want to go down. So everything I summarized up to now was the derivation of the things on this slide. So after we compute the rays, we do ray object intersection, and we have seen how to intersect our rays with spheres and triangles. And after the intersection, we compute color by doing 3 things, which are these. Let me get a new. So actually, you should be. This is a repetition of what you already know, probably, but I'm just talking about what I see. It's important for me. So after we compute the intersection point, the rest is, in order to compute this color, we actually do 3 main things. The first thing is executing the basic illumination model. The basic illumination model, which is ambient, diffuse, and specular. We have light sources in the environment. This diffuse and specular components belong to each of these light sources. They're computed for each of the light sources separately. And in order to add this diffuse and specular component, we also need to look at the ray from the surface point to the light. And check whether it intersects with other objects. That's the second thing that the second main thing is shadows, whether we are going to this light source has a contribution in the diffuse and specular components. And the other thing that makes this ray tracing algorithm recursive are reflections. So reflections are basically reflections from other objects. So we reflect this ray with respect to the surface normal. And we ask the same question recursively again, as if this is a ray which passes through the center of a pixel. We ask, what color is this ray? So we do the same computation for the other object and also add this contribution depending on the mirror reflectivity of the surface. We either incorporate the entire color, reflected color here, or we just add a certain percentage of that depending on mirror reflectivity coefficient. Also, other things here that you may think about is the distance of the light attenuation with respect to distance. as the distance of the light coming to this surface increases, we may have different decrease functions, and whether quadratic decrease or linear decrease in the amount of light that is coming to this. So that's one thing that you can do for realism. But basically, that's the whole ray tracing algorithm. And then we have talked about different data structures to represent objects. We have seen an indexed face structure in which we have vertices listed separately and given indices first, and then faces, which are basically either triangles or quadrilaterals, are indicated by using these indices to the vertices, which is an efficient way to represent them. We have seen some data structures to speed up the scene representation, like we have seen oak trees, binary space partitioning trees, and there was one other data structure to write oak tree, binary space partitioning tree. What was the other one? Let's go. Yeah, KD tree. Yeah, we had the KD tree, in which the difference is that in oak tree the branching factor was 8. In KD tree the branching factor is 2, and we alternate between dimensions. So every every third depth we go back to the original coordinate variant. So x, y, z, x, y, z. So yeah, thank you. So we had KD tree. We had oak tree. We have seen oak trees, and yeah, binary space partitioning trees. So these are space organization structures that we have covered. And we have talked about texture mapping. So let me in texture mapping we have seen two main algorithms and two main points: the nearest neighbor, and we had the bilinear interpolation. So yeah, texture mapping was the second thing we did. So texture mapping, the idea is to map to the image, to give different reflectance coefficients, to give different colors to different points on the surface. That was our main goal in texture mapping. And for that, we need to provide a mapping between a given coordinates, x, y, z coordinate on that image. So we have worked this out for spheres, how to map a sphere being a two-dimensional manifold. Also can be represented by two parameters. So for that, if we use the parametric representation of the sphere with this theta and phi, if we find what theta and phi is, they can easily be converted to these UV coordinates on the texture. So in other words, for example, U coordinate goes from here to here, V coordinate from here to here, maybe. Okay, so V is from top to bottom. So if we have this texture coordinate space, as you can see, this changes the angle. If we go left to right on this image, it tells you how you rotate around the equator. So these 360 degrees that you have here, which is indicated by this phi angle, could be turned into your U coordinates. Okay, as you can see, phi, which is between 0 and 2 pi, is just turned into, actually it's between minus pi and pi. The way you write the equation, the boundaries of these angles may be different. Here, the way we define this phi angle, it may be minus pi or pi, as I can see, because we add pi to that, so it becomes 0. Then it becomes between 0 and 2 pi. You divide it to 2 pi, it becomes between 0 and 1. So this is just a linear conversion from those angles from 0 to 2 pi to 0 to 1. And also this theta angle, the way you define it, it's when you're at the North Pole. At North Pole means that, as you can see, you're at the top of this image, and South Pole, you're at the bottom of this image. So as V changes from 0 to 1, your angle theta changes from 0 to pi. So the only thing you need to do is rescale it, divide whatever your theta is, divide it by pi, you will get some value between 0 and 1. So you just have a texture mapping is mapping between the coordinates of your points or your parameters to coordinates on the texture. And when we do these things, for example, when we find U and V, the texture coordinates are usually real valued, floating point values. So another thing we need to solve is that our images, our textures are discrete integer coordinate pixels. How do we find which pixel color to fetch? So the other operation that we need to do is fetching a texture color. So fetching a texture color from a discrete image like this, we have two main strategies. One of them is just round whatever you have here. And here, these slides are the ones that are modified by Ozoja. I mean, we didn't actually think about when we say u is equal to 0, 0 here, v is equal to 1, 1 here. The image coordinates, the pixel coordinates actually do not correspond to this 0, 0, for example. The 0, 0 u, if you just think about it as the pixel center, 0, 0 pixel, there is a small deviation at the ends of these textures because the 0, 0 uv coordinate does not indicate the center. It doesn't start with half pixel. It's like the entire texture is half pixel moved to left and down if you treat 0, 0 as your pixel center. But 0, 0 here indicates the top left corner of your texture, image window. Just like image windows, we need to have this half pixel width type of thing. So whatever we compute here, after we multiply them with nx and ny, we can subtract 0.5 from these values so that now it corresponds to directly, uv now corresponds to the top left corner of your image window. So yeah, this small modification, I mean, it wouldn't, if you didn't do this, you would probably not even see the difference because it's really, when nx and ny is really large, if you have large textures, 2000 by 1000, what happens in half pixel, this half pixel deviation would not be something noticeable. Okay, but for mathematical correctness, so the texture is updated like this. So in this way, if you multiply, if you do this subtraction allows UV actually 0, 0 maps to these coordinates here, and so the pixel centers are now correctly maintained. So in nearest neighbor thing, the fetching of the texture is just by whatever the real valued floating numbers we have, we just round them. Get the closest pixel. In bilinear interpolation, we look at the 4 neighboring pixels, 4 pixels that are surrounding our real valued ij, and we do an interpolation. It's like we're averaging these 4, but the averaging is done in such a way that it takes into account the distance of ij, the actual real valued distance of ij to these pixel centers, horizontal and vertical distance is taken into account. The formula is basically this. Okay, since you don't need to memorize any of these formulas because since the midterm is going to be open book, so you can just, if you have questions about this, just refer to these slides to solve these problems. Yeah, and how can we use texture color? We can use texture fetched color. Can be used as the diffuse reflectance coefficient, or it could be directly replace the color you compute. So what you're going to do with this fetched texture color should be indicated as a parameter. It's something that user may choose, or if we ask a question about it, we should definitely indicate what this texture color is going to be used for. Okay, so there are various ways you can use this fetched texture color, whether it's the diffuse reflectance coefficient or the entire color is replaced. And this one replaces the diffuse color completely with no normal vector adjustment. But if you just replace the reflectance coefficient, the KD component, and compute the color, take into account the normal vector of the surface, we are going to have a more realistic representation. So yeah, we have also seen texture mapping triangle. We have seen barycentric coordinates. Basically, when we have when we're trying to map a texture to a triangle, what we do is, if we have a point here inside, we find the barycentric coordinate of the point inside the triangle. Those alpha, beta, gamma is going to be the the the fetched coordinate. Okay, so the UV coordinates basically are found by so each triangle corner is mapped to a pixel. Like they have UV coordinates. So the problem will be, if I have a point inside a triangle, what will its texture coordinates going to be? So we find the barycentric coordinates of these points, alpha, beta, gamma. Then the UV coordinate of the point will just be a weighted average of the UV coordinates of the vertices. So which tells you that in order to have texture mapping in triangles, somebody has to give us as input the texture mapping at the triangle vertices. So triangle, this is like an input to us. At the triangle vertices, the UV coordinates are known, or whoever modeled this whoever constructed this model should also, when the texture is mapped by using these programs like Blender, 3D Studio Max, the texture mapping output maps texture coordinates to each triangle vertex. So that's something that we already know. We talked about some additional information which I'm going to skip. Well, yeah, this is in these updated slides. There's also like some effects that I didn't have in my original slides. These smoke or cloud effect is coming, for example, from procedural textures. And after that, we started talking about modeling transformations and viewing. So just two sets of slides remaining up to this point. But why do we do these modeling transformations and viewing transformations? Actually, I believe maybe if immediately starting talking about modeling and viewing transformations, maybe we should have talked about the second algorithm. The forward rendering pipeline will be an alternative to ray tracing, that we are going to see a second algorithm which also gets a virtual world and looks at it with some camera and takes a picture of it. So the second part of the course is going to concentrate on the second algorithm, which is called the forward rendering pipeline. Forward rendering pipeline, very well-known popular algorithms like OpenGL. I mean, all games we have been playing up to now these days. I mean, now there are new games which also uses ray tracing, but the gaming industry, OpenGL, and was dominated by these two libraries, OpenGL and DirectX. And they are both an implementation of this forward rendering algorithm. And unlike ray tracing, the algorithm is this. Given a virtual object's vertex, we ask this question. So our goal is, for example, if this is a triangle, imagine, I mean, instead of complicating things, imagine I have a three-dimensional triangle and I want to get a photograph of it. So this is my image window, and I have, for example, a blue triangle that I have here in three-dimensional space. So this is, I have an XYZ space. Maybe these are my coordinates. This is my coordinate system where this is 0, 0 maybe. Okay. Now our goal will be how would we see this triangle on this image window? Okay, maybe if it's some kind of a field triangle. If you take a picture of this with this photograph, with this camera, what are you going to see? Our goal is to, this is the basic rendering problem. I mean, if you solve this for a single triangle, if you have a nice solution for a single triangle, actually you can just increase the number of, just make your scene complex. Your image also looks is going to look complex and nice. Okay, but let's try to in ray tracing, the problem is solved like this, right? I mean, I don't want to repeat everything from scratch, but what we do is we generate rays through every pixel of this photograph and this image, and then we intersect all of them with this single triangle, and the pixels that intersect, we compute the color and set the color to this. Now, here is the idea in forward rendering pipeline. We ask this question, this triangle, instead of, we don't deal with pixels in the first place, we just ask this question, given this, a vertex of this triangle, V1, which pixel, this V1, so this is the pixel that V1 is going to map onto, or which is the correct term for that is going to be projected on. So V1's projection on this image window is actually when a light ray, for example, comes here. It's, I mean, that's the same. This projection point actually is the same thing that we did for in ray tracing. If we had a ray that passed through this eye point and the center of this pixel, it would intersect or with V1. Okay. Or it will be very close to V1, because when we do this projection, it's not the V1 may not exactly project onto the center of the pixel, because after the projection we will have some floating point numbers on this image window. We didn't discretize it. In ray tracing, we start with discretization. We have the centers of the pixels that we send rays through. Okay, so the discretization is in the first step of ray tracing, where you generate your rays. Your rays are finite number of countable rays. You start with a discrete image. Here, we will do the discretization at the later stages. The first thing we do is which pixel or which coordinate on the image window, which real valued coordinate. Maybe we can then use the closest, just like texture mapping, we can then use the closest pixel to that coordinate to say that, okay, if a ray passes through the center of the pixel, it will pass very close to V1. But we are asking this question directly for V1. Can you find which pixel V1 is going to map onto on this image window? Can you do the same thing for V2 and V3? Okay, both of them were V. So this is V3. So after we find these pixels, the algorithm proceeds by with this. If I have an image which I know that the corners of the triangles are these 3 pixels, I want to draw a triangle that pass through these pixels. How do you do that? For example, we will first start, after the midterm, we will start with a line drawing algorithm, which by just using very efficiently, by just using integer addition and subtraction, nothing more, you will be able to draw a line with any slope, with some floating point, real valued slope line. We'll be able to have an algorithm that will figure out which pixels should be highlighted if you were to draw a line between these two start pixel and end pixel. Okay, so if the rest is, after you know the triangle's corners, the forward rendering algorithm proceeds by finding on the image space, on this pixel space, trying to figure out which pixels have to be illuminated and what color they are going to be. Okay, so that's the forward rendering algorithm. And this whole process, going from V1 to this pixel coordinate, could be done with these. For example, this V1, if you with modeling transformations and weaving transformations and projection transformations, by multiplying, all of these are 4x4 matrices. Okay, so by multiplying your V1 with a single 4x4 matrix, so you can combine all of them together, you can solve the first part of the forward rendering pipeline. So this is sometimes called vertex processing. And as you can see, the 2 weeks that we have covered, modeling transformations and weaving transformations, and projection transformation, we have seen all of them. So when I say weaving transformation, this is the camera transformation I'm talking about. But sometimes it's in OpenGL terminology, camera transformation may be referred to as weaving transformation too. I mean, projection and weaving transformation, we just name them together as weaving transformation, but sometimes it's only referred to as camera transformation. But these 3 matrices multiplied together is the vertex processing stage of the forward rendering pipeline. But the reason we are going to talk about forward rendering pipeline in detail after the midterm exam, but the reason we started with modeling transformation without even mentioning forward rendering pipeline is that these modeling transformations and also viewing the camera transformation too could also be used in ray tracing algorithm, right? In ray tracing, you may provide animations by, if you want to move objects around. For example, you want to have a ray tracing called the original model you have here. For example, you have these different, you have this auto car, which was an automobile that you rendered. Imagine you want to rotate the automobile around an axis that passes through its center. Okay, you want to rotate, you want to have, you want to generate many ray traced images, which then you may stitch them together by using FFmpeg. You may create a movie of a rotating auto car, but how are you going to rotate that car? Okay, and in modeling transformations, we have seen methods to do that. We have seen how to rotate, how to change the vertex coordinates of some object if you want to scale it, translate it, or rotate it around some axis. So this is what we did in modeling transformations. We have seen how we can do it, how we can do all these things. Basic transformations, translation, which is just movement, panning. Sometimes this is called, in certain contexts, panning. Just moving, taking away. If you move left and right, up, down, forward, backward, this is like panning something, and it refers to it's the translation that we are referring to. The other is scaling. You may enlarge an object, make it smaller, and rotation. Rotation takes in 3 dimensions. Rotation takes 2 main parameters, which is the rotation axis, which is given as a directed line. So your rotation axis is nothing but actually, it's a directed line. The direction is important because it tells you whether the angle theta degrees that you want to rotate is the positive theta is in which direction. So the direction that I have drawn right here, by using right hand rule, we're always rotating the counterclockwise. So along the ray, the counterclockwise, or in other words, if you just use your right hand, and if you use the 4 fingers of your right hand to indicate the rotation direction, and your thumb to indicate the positive, the direction of the rotation axis, the positive theta rotation will be in that direction. So therefore, the rotation axis, it's not just a undirected line, it's actually a directed ray like this. This is what rotation axis is. So we have seen how to form these 4x4 matrices, how we can compose them. We had some interesting questions, like, for example, if you have a mirror, which is, how do you get the mirror reflection? Find the composite transformation, for example, to find if I have a mirror, for example, which is just arbitrarily oriented, but it may be upright, for example. Imagine I have a mirror which its sides are upright, aligned with the y-axis like this, but its top and bottom sides, they are in the direction, for example, the vector that shows the direction of this, in other words, maybe, for example, 0.8, 0, minus 0.6. So it's in the negative z direction, as you can see, and positive x. Look at this. So this is a unit vector which shows the direction of the both top and bottom are in this direction, for example. And I need to also give this mirror has some location. For example, maybe this corner here is at maybe 3, 1, minus 1 coordinates. So if I have a mirror like this, and if I have an object in front of this, find the transformation matrix that will, when applied on the vertices of this object, will give me the mirror reflection that appears behind this. So, for example, if this is the mirror reflection that is going to appear behind the mirror, and you want to draw, you want to also render that here in your scene, how do you get this? So the thing that if you remember, what we can do is we know how to reflect, for example, with respect to the XY plane. Okay, so if this is the xy plane, reflecting with respect to xy plane is easy. The only thing you do is you invert your z coordinates. So the matrix will be 1 0 0 0 1 0 0 0 0 minus 1 0 and 0 0 0 1. So this is my basic reflection with respect to the xy plane. So what we do is in our composite transformation, we first move this to here. For example, this 3 1 minus 1 may be moved first. So I can just write it like this. Translate minus 3 minus 1 1, which will move this point to here. Then perform a rotation so that the rotation around y-axis, okay, such that this becomes your x coordinates. It's aligned with this one. So I think this rotation will do it. So let me form this rotation. We are rotating around y-axis. So my y coordinates do not change. So if I write this vector as my u vector, and this is 0 1 0 0, and if I write 0.6 0 0.8 as my z vector, I think this will perform the rotation. Sorry, this is 0 0 1. This will be the rotation matrix that I'm looking for probably. I mean, I will just have one of them as my z-axis and this x-axis. I'm going to write these vectors as a rotation matrix. I already know this is a unit vector, so this is unit orthogonal to each other. So it will perform a rotation around y-axis, which will align x with this and this with this. So this vector, which is this one, will be aligned with x. So I write it as the u vector here. The other one, this one, which seems like it's 0.6, 0.8 vector, 0.60, 0.8 vector. As you can see, all of their y components are 0. It means that these vectors are on the xz plane. Their y component is 0. And if you do this, perform the reflection, whatever this r is, undo this r with this inverse, and then move it back to its original location, 3 1 minus 1. This 5 matrices will perform this composite transformation. So we have seen composite transformations in that. And the final thing we did see was how to do this viewing transformation. We have seen 3 things: the camera transformation. In camera transformation, if you want to move from world coordinate system to camera coordinate system, what do? We move the camera coordinate system onto the world coordinate system, just like this one. We move the eye point to the world coordinate, then we do the rotation to align the camera coordinate axes with the world coordinate axis. This provides a transformation from world coordinates to camera coordinates. Then we have seen orthographic projection, which is actually mapping a rectangular prism viewing volume to a canonical viewing volume between -1 and 1. So this was just these were just on Tuesday, so I think they should be fresh already. So I think I don't need to. Maybe I can spend the last 5 minutes. If you have any questions or so, I will be happy to answer them. Then we have seen viewport transformation. After projection, the last thing was viewport transformation, which is just mapping from this -1 1 to the pixel coordinate system space, which is, let me just quickly go over the final slides. It was here. Viewing transformation as a perspective. Viewport transformation, the coordinates between 0 1 0 1 0 1 are mapped to your pixel coordinate system, but still they are still not integers, although we stretch it so that the top left corner is -0.5, the top right corner has the coordinate nx minus 0.5. So therefore what we have here is that still when we multiply a regular coordinate with these values, they are still going to be at the end real valued. Now in later stages in rasterization, we need to find the closest pixel center to these coordinates, just like in texture mapping. We are going to use the nearest neighbor approach to discretize those values before we start. We try to draw lines between them, or triangles that fill in the entire space in between these three values. Yeah, we talked about Z fighting, and that's it. Yeah, yeah, that's all I wanted. This was a recap of everything we have seen up to now. If you have any questions, I'll be happy to answer them, but I don't see any questions. So I hope everything is clear. So there's still like a couple of days until the midterm. So while you're studying, if you have any, if you stumble upon something that you cannot understand, please feel free to send us an email, okay? Ozoja and I, whoever, you can send an email to both of us if you want, or just me. Send us an email and we'll be able to get, we'll try to get back to you as soon as possible to answer your questions, okay? And that's it from me. Okay, thank you everyone. Good luck in the midterm exam. And also during the midterm exam, if you have any problems, technical problems or anything, again, send us an email and we will be monitoring our email during the midterm exam regularly, and we will get back to you as soon as possible. Okay, so the emailing will be the main communication mode during the midterm exam. If you have any technical difficulties, problems, please let us know by sending us an email during the midterm. Okay. I wish everyone a successful midterm exam. See you all next Tuesday, our Tuesday class. We are going to continue with this rasterization, the forward rendering pipeline algorithm. Bye-bye. Have a nice weekend. Bye. I will stop sharing now. Bye. İyi günler. Oh, let me stop recording.